I'm going to try a new setup here. I'm actually in my office today at work. I think this is going to work. I don't know. Let's see, shall we? So we're going to start lecture 10 here for us. This will be where we talk about equilibrium in three dimensions. Is going to be our focus. This is kind of the latter part of chapter 5, and the Hibbler text is what we're using. Equilibrium in three dimensions, we have up to 6 equations for each free body diagram. So as opposed to a two-dimensional free body diagram where I can write up to 3 independent equations, in a three-dimensional free body diagram I can write up to 6 independent equations. Right, so I can write in vector form, you can say that the sum of force vector should be 0 if a body is in equilibrium. And that means that if I add up all the forces in the x direction and all the forces in the y direction that have a j attached to them, and all the forces in the z direction with a k attached to them, all 3 of these sums have to be 0. And if you equate coefficients, that just means if I add up all the x direction forces, I can set those 0. We've already done this, right? Add up all the forces in the y, I can set those to 0. Add up all the forces in the z, set those to 0. Again, now we've already done that. What's new, because now we've covered in chapter 4, we've talked about the moments. I can take the moments about any point or any line or any location within that free body diagram. It doesn't have to be the origin, it doesn't have to be point O. I can take the sum of moment vectors at any point, and for it to be in equilibrium, meaning it's not rotating, or at least it's not changing rotational motion, that sum of moments needs to also be 0. Meaning that if I take the sum of moments in the x direction, all the moments about the x-axis, those should be 0. And then same thing about the sum of moments in the y direction, or about the y-axis, if you will, or directed in the y direction, those should all add up to be 0. And the same thing in the z. If I add up all moments, or torque, torque for the physicist, or if I'm dealing with motion, if I add up all of the moments in all 3 directions, those should be 0. And again, 6 equations, meaning I can pull each one of these. I can say, sum of forces in the x, that has to equal 0. Sum of moments in the x direction, that has to equal 0. And do the same thing in the y. Same thing in the z. Sum of forces in the z direction have to be 0. Sum of moments about the z-axis or in the z direction have to be 0. 3 equations, 3 more equations, up to 6 equations for each free body diagram. Now don't forget our process we talked about previously. Generic problem solving. Right? What are you looking for? What is known? That's where you draw a free body diagram. What laws, equations, relationships do you have? We have these, right? So those are what equations I can use. Do I have as many equations as I have unknowns? Do I have everything I need? If you have more than 6 unknowns, or they're not, the unknowns that you need are not on the particular free body diagram you drew here, then that's a no. You go back and, okay, well, what's left? And draw a free body diagram that incorporates the things that you're still looking for, apply equilibrium to it, hit a point where you have as many equations as you have unknown, and solve. May you not have more than 6 unknowns you're solving for, but I mean, we are engineers. We're not mere mortals. We do solve for many, many, many unknowns on a regular basis. So don't worry too much if you do have more than 6. But rest assured, on my exam problems, I try to limit it to something that's doable. When I give you a 3D problem, I would prefer to give you something that's doable in a reasonable amount of time. That's my philosophy. Now, we talked about, when we talked about two-dimensional reactions and how do I know what forces and moments are applied with a two-dimensional reaction, and we said it really kind of comes down to what what type of motion is stopped or prevented if a connection or reaction stops what we call translation motion. That's sliding motion or linear motion, if you will, or just what we would often just refer to as movement. Or movement in a direction, meaning X, Y, or Z. The connection must apply a reaction force in that direction. And that's, again, very similar to what we saw with two dimensions. In our text, as I'm sure many other texts, you'll find often a table that would say if you have this kind of connection, if you have a pin connection, well, it's going to provide a force in the X and a force in the Y, a reaction force in the X and a reaction force in the Y direction. And you'll find a comparable table to that in your three-dimension section of your text. That's true in our Hibbler text, and that should be true in just about any other text. You will find a table that basically breaks this down for you and says, here's some common types of connections. Here are the forces that, the reaction forces that type of connection will apply. And you will find in 3D, what you will find is, when we look at 2D, there are very rarely reaction moments. But in 3D, there are often many more connections that will have reaction moments. In fact, some of the common 2D reactions, like the pin, for example, or the hinge, for example, the hinge or the pin will have reaction moments we will have to compute in 3 dimensions. So if a connection prevents rotation about an axis, it imparts a reaction moment about that axis. What do I mean by that? Let's see what we mean by that. L10, page 2 of something. What do I mean by that? Let's say that I've got a pin connection or a hinge of some type. Pins and hinges are kind of synonymous. Basically, I'm going to try to draw this in 3 dimensions freehand, which is a bit of a challenge, but I think we'll get there. Right. So something, I've got maybe some sort of structure comes out, the pin passes through it, and then on the other side, it's a very terrible drawing. Right. Not a good drawing. Hopefully this gets the point across. So let's say that this is the x-axis. Let's say the pin is in the y-axis, the y direction. Looks like a taco, doesn't it? Sorry. And let's say straight up, of course, as always, is the z direction. What we're saying here is if we call this A or the origin, if I were to replace this, and if you look this up in the tables, you would find what it actually then applies is right here. You would have forces in all 3 directions. You would have AX, you would have a reaction force in the AX, a reaction force in the Y, and a reaction force in the Z, because this pin cannot come apart and you can't move it. Like if I grab on this, whatever this is attached to up here, I try to pull it up in the Z direction, or I try to move it in this X direction, or I try to move it back and forth in this Y direction. It won't move. It's locked in because it's pinned in there. So I've got a reaction force in all three directions. But what is not a little harder to see is think about how can this rotate? What direction can this rotate? Well, I can rotate it kind of back and forth about this y-axis, the direction of the pen. It can be rotated in that direction. But what I can't do is if I try to spin it right about the z-axis, there's no spinning about the z-axis. I can't spin this thing vertically, so there's a reaction moment in the z. And it also, if I try to rotate it about that x-axis, it won't rotate about the x-axis. I've got a 3D printed hinge here. I'll show you. Maybe that helps. Right. I also have a reaction moment in the x-axis because I can't rotate this thing about the x-axis as it's setting right now. Hopefully this kind of shows up. So a little better. I should have drawn it. I should have drawn it more. I should have just set this next to me and drawn it like this. But let's say, so you see the pin is in here, right? You got this pin in here, and it can rotate about this pin, but it can't rotate. There's some slack in there, so it printed. So I can't rotate it about the vertical axis. I can't rotate it about. So if I put this kind of in the direction of what I've got drawn there, right? So notice, because the pin is in this y direction, I can rotate it about the y-axis. So there's no moment here in the y direction stopping the rotation. It is allowed to rotate in the y-axis. However, if this is my x-axis and I put the pin, notice the pin is in the y direction. Now that doesn't mean whenever I've got a hinge or a pin that there's never a rotation, there's never a moment in the y-axis. That's not what it means. What it means is there's no moment in the direction that the pin is. If the pin, this guy in here, right, the point of rotation, if that is pointed in the y direction, that means there's no reaction moment in the y because it can rotate about the y. But the other two directions, notice if I try to rotate this thing about the x-axis, it won't rotate. Right? It hits a stop, and it stops it from rotating any further in the x-axis. That's because there's a reaction moment applied in the x direction. And if I try to rotate this thing vertically about the z-axis, notice again I can't, if the z is this up and down direction here, and I try to rotate it about that z-axis, there's no rotation because we're applying a reaction moment to prevent that rotation. Hopefully that helps it. Drawing it's one thing. You got to be able to draw these kind of in 2 dimensions so you have an idea what you're dealing with. But sometimes it just really helps to just see one in the flesh. Now notice if I rotated this thing, let's say we put this where this we put the pin in the z direction, right? So if the pin is in the z direction, it's allowed to rotate in the z direction, right? But I can't rotate it in the x, so there's a reaction moment now in the x, and I can't rotate it about the y, so now there's a reaction moment in the y. Again, it's not anytime you have a pin, you don't have a reaction moment in the y direction because that's how Professor Fowler drew it the first time. No. That's not what I'm saying. The direction that the pin, whatever axis you put the pin in, that is the axis where you do not have a reaction moment. If this thing needs to rotate, and I put my pin now in the z direction, well, now I can rotate about the z-axis, so there's no reaction moment in the z, but there's going to be a reaction moment about y and about x. Okay. Hopefully that helps. Again, seeing a diagram of it, maybe I don't know how much that does help, but actually, maybe seeing something in the flesh, maybe that helps a little bit. A common type of reaction you might encounter in 3D, let's say I've got some kind of a plate or like the edge of a table or a book or something like that, and I just put a roller underneath it, just a ball or a point of contact, and it's on top of a smooth surface. So the only thing that's going to be applied in that case, just like in 2 dimensions, you're going to have a normal force, and that force is going to be perpendicular. It's going to be perpendicular to whatever surface applies it. So the direction is set, and it can only apply a push force. Whereas with a pin, these could be pushing or pulling. I've drawn all of them in tension, pulling, but they can push or pull because, notice, I can push or pull this thing in the X direction and it can apply back or forth. But if I've just got some sort of contact point, right, so I can move it back and forth. Let's say that this is my X and my Y, so to speak, and the Z is straight out of the page. Now I can pull this up and there's nothing stopping it from coming up. But what there is, if I try to push it into the page provides a normal force pushing back. So a normal force, or a roller, right? So this is true for a roller, what we sometimes will call a rocker. This is, basically any kind of small contact. Any of those can only provide a normal force. And it can only push. But if I've got, as we said, here I've got a hinge, and this is pin. That's with the pin in the Y direction. Then it's like this. Whatever direction the pin's in, there's no reaction moment in the direction of the pin. Okay, look through the table in your text that talks about these different kind of reactions. I'm going to talk about a ball and socket joint in the next video. I try to keep these to 15 minutes. I'm a little bit over. So I'm going to stop and go to the next video.